All right. Can everyone see my screen?
Yes.
Okay, awesome. Aloha, everyone. My name is Wilson Chow, and today I will be presenting to you the Hawaii Energy Nexus, which is an inter-island petroleum and freight supply chain fragility analysis. I built a dashboard for this, and this research was developed under the Cyber Infrastructure Pacific Professionals Program and in partnership with Hawaii Data Science Institute and Pacific. So a little bit about me is that I am currently a data science and economics major. I was originally born in Vietnam, but have been raised in Maui, Hawaii all my life, and a Maui high school graduate. So within living on Maui all my whole life, I've noticed a few common things that really struck to me. One was that I've watched how my family and community pay for some of the highest fuel and grocery prices in the country due to the Jones Act, and particularly the reason that we are isolated from the rest of the mainland and mostly the world. And to find out these solutions, I wanted to use real math to explain why these outcomes came to be. So within my team, the Bulls and the Bears, both myself and my research member Anthony were both heavily into economics. So we thought, why not tailor our projects to economics? So for my specific project, I leverage public U.S. government data, specifically FRED, and to use reproducible in-browser mathematics. So within this, I also looked at economic reality. So whenever regarding to translating abstract global oil fluctuations into these localized real world impacts for Hawaii residents, I wanted to make sure that it was impactful for people within my community. So the reason for this dashboard was to mainly present findings in plain languages so that other policymakers and analysts can use it without really needing a PhD in econometrics or being able to see all these vulnerabilities at ease. So the mission between this project was to figure out why Hawaii's fuels had so much volatility. So one of the reasons that I really wanted to answer was Hawaii is so physically isolated, and we want to measure that vulnerability between dollars and barrels. And so when global prices of oil does increase or have a pump, how much of that shock really reaches us? And then secondly, which physical single link in our supply chain does break down when it does have a lot of damage? And to answer these two core questions, this is what my dashboard hopefully answers. So within this, here are a few of the findings that I did some background research in. So first, we import about 90% of our energy across the ocean, and there is typically a zero pipeline redundancy. So there's typically not a connection to the mainland that exists. So every drop you typically comes from a ship. There's also a single point of failure. So only one active refinery in Hawaii, which is the Kalaloa, that processes the entire state's fuel supply. And fourth, we also have the Jones Act dependency. So the Jones Act was a 1920 federal law that requires all cargo moving uh, short ships between U.S. ports to travel only through the U.S. and U.S. owned and U.S. crewed ships locations only. So this law really destroys inter-island shipping, and it causes this Hawaii premium that we're seeing today. And when it comes to international shipping. So putting all these factors together, Hawaii pays a large premium per gallon. So some historical context, if you look at this chart of across the 30 years of Hawaii's gas prices, there were three pivotal peaks. So one was in the 2008, which was during the global financial crisis, as well as 2012, where the post-crisis had a squeeze. And then from June 2022, there was an all-time high due to the post-pandemic inflation and also combined with our Ukraine conflict in the US. So what this chart proves is that the volatility isn't really random. It's very persistent and structural, and it really follows a lot of geopolitical news. And the severity can really detrimentally hurt us if we don't have a way to predict what's going to happen next. So my solution was the Hawaii Energy Nexus dashboard. And within this, there was three design principles. It had a self-contained architecture, so everything was ran through a browser using vanilla JavaScript. and there isn't really any complex backend. There was also live data integration using FRED, the St. Louis Federal Reserve, and EIP, which is the Energy Information Administration, and then also a dual audience design. So it's very plain language. So hopefully the general public can look at this and verify the work right through the dashboard. So I'm going to talk more about data pipelines. So within this, I used a bunch of public domains or APIs, two from FRED and EIA, one from the Bureau of Labor Statistics to cover WTI crude, Brent, CPI, and also Hawaii's typical gas prices. And then within this infrastructure, there is a compliance API key server side. And then whenever the network ever fails, there seems to be a seeded random snapshot that the dashboard always relies on if anything does go wrong. And within this tech stack, there's a self-contained HTML and JavaScript running the client side, so there isn't any black box in the back end. So here are the few major findings. Within 2 months, there's typically a lag. When crude oil price happen, especially when it comes from the Strait of Hormuz, for example, it takes about 2 months to navigate underneath South Africa and into one of our ports in Florida, and that's where it gets distributed to the rest of our states. And so knowing this, this pass-through actually causes a 53% transmit across local consumers. So every dollar in global crude, there's actually a 53% increase that is absorbed through refinery margins and retail pricing along the way. So having this being very close to 0.59, this predictive confidence, this model explains that 59% of the variance in Hawaii's gas prices are held in test data. And so this model has never been seen before until it was crossed into a two-variable model. So how did I get this numbers? So what I used was a vector autoregression or VAR, and it's the same class of math that the Federal Reserve uses to trace how interest rates changes and ripple throughout our economy. And so if you can see at the peak of 2 months is when the shock hits the hardest, and total area under the curve is the pass-through percentage. So rather than using isolated formulas, the algorithm tracks crude and local gas simultaneously and automatically maps the shock cascade throughout the voyage delays. So now the second major finding was the physical breaking point. So within 1,000 barrels per week, that's the system that absolutely measures the absolute capacity that the most of the fuel from the inter-island barge network can possibly sustain. So for example, the Honolulu is noticeably the true choke point where even a single disruption can actually eliminate 100% of our neighbor island supply all simultaneously. So not even 50%, not even 80%. There's also 34,000 barrels per week that is exposed to our second largest population, which is in Maui. And so that carries a large allocation already off the bat. So how did I find this choke point? So I used the max flow min cut graph theory, specifically the Edmonds-Karp algorithm. And this yellow node is the Honolulu harbor or hub, and it points to where the capacity limits and the smallest sets of the pipes need to be cut off for the entire flow to no longer work. So in the future, I would like to continue this dashboard with a deployed serverless FRED API so that it has a more stable rate limit when it comes to friendly autonomous data paths. I would also like to integrate Rio Young Brothers published barge tariff schedules, since they are one of three the largest shipping companies across Hawaii, and also integrate AIS vessel tracking like SPY or marine traffic, or even partnering with NOAA, so we can look at current international flagging problems and detect them before they even disrupt our whole economy. And lastly, I want to thank everyone who made this possible, the SCIPE program instructors in our cohort, the National Science Foundation, UX Educational Systems, and the Hawaii Data Science Institute for their resources support. I also want to especially thank my mentors, Aaron and Marissa, for their invaluable guidance, and especially my group member, Anthony Zong, for his dedication and hard work throughout this project. And for everyone else who's pulled everything through, this would have not been possible without all your help. And this is my full reference list on this slide. And so if you'd like to look at my methodology, I have this published throughout GitHub, so you can actually pull this through, and I believe it should be attached later on. Thank you so much for listening to my presentation.
Very nice. Thank you. Very timely, as Luke says. A little bit of a jam. I wonder if we did the same thing in analysis in Iran, what the figures would look like. Does anybody have any questions? I have a one question. So, do we have access to military oil reserves, or is that sort of off limits? Do you know any policy around that at all?
So yeah, so the oil reserve, I believe there is actually a rough estimate or like more of like a rough uh data that's out there. It's not currently something that is being lively tracked as such as the that is given out, such as like the US Information Administration, where they have stuff that comes out pretty much weekly or monthly. So we do have a rough estimate, but it doesn't isn't actively being lived and displayed out for the public to use consistently.
Probably a security thing, isn't it? You know, so want
Yeah.
the rest of the world to know. All right. Thank you very much. Does anyone have any other questions? Okay. Thank you.